Hi everyone, and in this video I'd like to show one example of how topology and complex analysis are deeply related. Now, point set and algebraic topology set up a lot of deep and beautiful results in complex analysis. Sometimes these go without mentioning on a first course, and I wanted to bring up this particular example because it serves as a particularly striking limitation on one of the most powerful theorems you'll see in basic complex analysis. So to get started, let's look at this topological property, which is simple connectedness of regions. So we say that an open subset of the complex plane is simply connected if we can intuitively always deform paths in the space. So for example, let f and g be two paths, that is, continuous mappings of the unit interval, in U. We also want them to have the same endpoints to really consider deforming one into the other. Now, let's contrast these two regions below. One of them will be this open unit disk with radius 1 and centered at 0. If we take any two arbitrary points, here chosen in red, we can always pull one into the other continuously, and this will be fine no matter what points we choose or what paths can be taken between them. However, something as small as removing a single point, here the origin, from that region, can drastically alter its topology and the kinds of analysis properties that we will look at from it. So this region on the right-hand side is the punctured unit disk of radius 1. It's the same as on the left, except now we're removing 0, so 0 does not lie in the set. Now if we take two arbitrary points, let's say diametrically opposite, and paths between them that lie on either side, there is no way to continuously deform f into g without passing through this hole in the center. However, the hole in the center does not lie in the set anymore, and this is not allowed. So there's no way to do this while remaining in the set U. For simplicity, we're going to denote the unit disk on the left-hand side by delta, and we will denote the punctured unit disk by delta star. Okay, so this is a foundational topological property, and we will show why it is so surprisingly massive and fundamental in a certain theorem, and what happens if we actually lose that assumption. Now we will look at something called a conformal map between regions. So let U and V be non-empty open subsets of the complex plane. A map from U to V is called conformal if it is bijective, so just injective and surjective as sets, and it is holomorphic, that is complex differentiable at every point. And one important property that comes out of this actually brings up geometric intuition to the picture, where it turns out that conformal mappings can be thought of as preserving angles locally. Let's say we have a point where two curves pass through and form an angle. A conformal map will not disturb this angle too much in the image. So this is important when we look at the Riemann Mapping Theorem in a second. In this case, when there exists a conformal map between two non-empty open subsets, we say that these sets are conformally equivalent. Now, it becomes an interesting question to ask, when can we find conformal equivalences between open subsets of the complex plane? Well, open sets abound in C. We can take them as nice as the open ball of radius 1, or as wild as something like the Koch snowflake, which has fractal boundary and infinite arc-length perimeter, and so on. But it turns out that even these kinds of wild sets, if we assume simple connectedness, can be geometrically realized as conformally equivalent to the unit disk. We can somehow smooth them out by taking this function, which maybe is not constructively defined, but it's still conformally equivalent to the unit disk as long as it's simply connected, and this is quite surprising. So this is the content of the Riemann Mapping Theorem. It states that any non-empty, simply connected open subset of C is conformally equivalent to the open ball of radius 1. This is quite surprising in its breadth because, as we mentioned just a second ago, you can take these wild open subsets, like the ones with fractal boundary, yet there exist angle-preserving maps, so somehow iteratively getting closer and closer to smoothing them out on the outside to the unit ball. Now, the appearance of simple connectedness here might seem kind of strange. How does this enter into the picture, and what changes if we remove that assumption? Well, the rest of this video will be dedicated to when this theorem fails, and spectacularly so, if we remove this assumption. It turns out that this is so fundamental that even if we take the most obvious examples of punctured disks or donuts or holes in the plane, then these regions cannot be conformally equivalent, and we will disprove, in fact, that a conformal map can exist between two such regions. The problem is as follows. Let A denote this region over here, which will be the annulus of inner radius 1 and outer radius 2. This consists of all points that have modulus between 1 and 2, and I have sketched it below over here on the right-hand side. It turns out that the punctured unit disk and the annulus are not conformally equivalent. So just by introducing this small puncture, we cannot find a conformal map between this punctured unit disk and the annulus pictured below. Well, how can we disprove such a claim? This proof is in a few steps, and by and large, the main idea is that we prove it through contradiction, and we use 2 or 3 auxiliary facts along the way. So we're going to suppose, for the sake of contradiction, that there does exist a conformal map from here to here. Well, our first idea is we have this function that is defined on this punctured region. Is there any way for us to extend it so that it's holomorphic on the whole disk? And the answer is yes. This is due to a theorem of Riemann called Riemann's theorem on removable singularities. It states in general that if a holomorphic map exists at all but one point in an open set, you can extend it to fill its value on that point. That is, it can take a value there such that the function is still holomorphic, and it is defined now on the whole region. This is possible if it is locally bounded. That is, you can find some small neighborhood about the point where the image is not arbitrarily large. You can bound it. Such a scenario here is perfect for the Riemann theorem because the image of this disk is naturally bounded of itself. Here, if we take some open subset that is about the punctured origin, then obviously it is going to map into a region that is contained within the annulus. The annulus itself is bounded by 2, because it consists of all complex numbers with modulus less than 2, and we can contain the image very easily. By this explicit bound, we can take f and extend it so that its value here at 0 still makes it such that the extension is holomorphic on all of the disk. So this is the construction that we embark on below. Let us say that big F is the holomorphic extension of little f from the punctured unit disk to the whole unit disk. And for now, we will say that big F maps the whole unit disk into the complex plane, but we will specify the codomain and the image of big F more precisely later on. How do we proceed from here? Well, our next claim is sort of a mini result that guides us along the way. This result states that this new holomorphic function we've just defined on all of the unit disk is in fact injective. How do we show this? Well, we argue by contradiction once again. We suppose that W is some point where F fails to be injective. Now, the only way for big F to fail to be injective is if one of the points involved is 0. This is because otherwise we would reduce to this little function f here, which is, by hypothesis, conformal, bijective, hence it is injective. Now, since little f is injective, it means that one of the points for big F has to be 0 if it fails to be injective, and the other point is going to lie elsewhere in the punctured unit disk. Now, let's consider 2 open sets. One of them is going to be an open ball about 0, and the other is going to be an open ball about z, the 2 points which have the same image under F. We can take these 2 sets to have empty intersection because under the metric topology, the complex numbers have Hausdorff property. So distinct points have disjoint neighborhoods in general. in a pictorial format, this is what the situation might look like, where we have this red point being 0, and we have this green neighborhood u, we have this other point in the punctured disk, which is z, and we can find some disjoint neighborhood v about that point. Now we can consider the two open sets as well as their images under F. So we're mapping the whole sets u and v under F. And we can ask the question, what can we say about these two sets, f of u and f of v? Well, the first thing to notice is that by the open mapping theorem of complex analysis, both f of u and f of v will be open. What's a consequence of this? Combined with the fact that they are obviously not disjoint because w by hypothesis lies in their intersection, we know now that not only do there have to exist infinitely many points in that intersection, that is, f of u intersection f of v even minus that point v in common is not empty, we can find z1 and z2 as follows. So because this intersection, even removing w, is not empty, we can take some z1, which is in u minus 0, and z2 in v minus z, so excluding even the possibility of these 2 points here, such that f maps z1 and z2 to the same complex number in the intersection of f of u and f of v. Well, why does this not work? What's the contradiction here? This is because since z1 and z2 are not equal by construction, since u and v are in fact disjoint, and that they both lie in the punctured unit disk, this reduces to little f, but little f cannot map z1 and z2 to the same point if z1 and z2 are distinct. This is because f is injective by hypothesis. This leads to a contradiction and shows that the function big F is injective as we desired. Now, what does the remainder of the proof consist of now that we've shown this auxiliary result? Well, we can now specify more precisely where 0 gets mapped under F. Obviously, by continuity, we know that 0 is going to be in the closure of A. This is a generic fact about metric spaces, and you can think of taking a sequence in the punctured unit disk that converges to 0. By continuity of F, it has to converge to either some point in A or a limit point, that is, a point on the boundary. Now, the boundary consists of the union of the two circles where the modulus is equal to 2 or the modulus is equal to 1. So these two closed sets. However, by the injectivity of big F, we know that f of 0 cannot be in the interior. Why is this? This is because we have the idea that the conformal map exists from the punctured unit disk to the annulus. Now, if 0 gets mapped to a certain point, then we also know the inverse image of any point in the annulus corresponds to a point in the punctured disk other than 0. This would mean that both 0 and that point in question get mapped to some point in the interior of A, which would contradict injectivity, which we just showed. This means that if f of 0 is not in A, it must be in the boundary of A. So we say that f of 0 is either on this exterior region over here, or it could be of modulus 1. Let's carry through the rest of the proof. Let U be an open neighborhood of 0 in delta. By the open mapping theorem, we know that f of u is going to be an open neighborhood of 0 in the annulus. What does this look like? Well, here, if we take some open neighborhood about 0, this gets mapped to a neighborhood over here. We can see pictorially that because 0 is on the boundary, or if it's over here, there is some small region of the open set that lies outside. But this is not possible if we have f of u in the intersection of the complement of the closure of A. This is a lot of words, but just everything outside this region over here and everything within this disk over here is the complement of the closure. And some part of this image over here has to intersect that. It has to lie in the complement. This is non-zero, non-empty. But this is a contradiction because by the continuity of f, we know that it has to map the whole punctured unit disk, that is all the values outside 0 but still inside this green ball, to points inside the annulus. Hence, no such function little f could have existed in the first place, and this gives us our result, that this punctured unit disk and the annulus are not conformally equivalent. So let's recap what we saw. Simple connectedness is a topological property that has to do with deforming paths in an open set, or looking at whether there are punctures that mess with the topology or the analysis of a region. The Riemann Mapping Theorem states that any non-empty open subset of the complex plane that is actually proper, so also not the complex plane itself, admits an angle-preserving or conformal map to the unit disk of radius 1, as long as it is simply connected. What happens when we relinquish this assumption? The theorem spectacularly fails when we have these two regions, like the punctured unit disk and an annulus of inner radius 1. In fact, any numbers would do here, because simple connectedness is so fundamental that you cannot let go of this hypothesis. Even very easily described regions such as these fail to have conformal equivalence between them. So thank you for watching this video, and I hope to see you in the next ones, where I will be discussing more interesting properties of complex analysis, how it intersects with other kinds of analysis, like results like the fundamental theorem of algebra used by Fourier analysis. We're going to look at maybe the proof of the Riemann Mapping Theorem and so on. And this is going to be probably a full-length series. So thank you for watching this one, and I hope to see you in the next ones.